Lesson 5, it says more C of M. Who remembers what was C of M in a brief for? Yeah. Conservation of momentum. Again, hopefully, if nothing else, hopefully I've taught you to abbreviate in your notes. I think that's a smarter way to do things. We've been talking about crumple zones and how the key to minimizing injury in a car accident is to increase the time of the collision, because what will that lower? What does damage in a car accident? Yeah, it'll lower the acceleration. Are you okay if I just put an A with a vector sign as my abbrev for acceleration? How many of you seen those little smart cars driving around that are very, very short? The tricky part there, Dina, is you don't have much car material to build a crumple zone. And so the engineers were clever. They actually made the engine the crumple zone. Put your pencils down, look up. So this is going to be a smart car crash test. Go out here. Hang on. Pause. Got to start at 5 minutes. Right here. So what we have is a smart car, and we're going to remote control pilot it. So it's going to be driven by remote at 70 miles an hour, which is about 130K, very fast, into a cement barrier.
70 miles an hour to naught in 1 second. The little smart hit with such energy that it moved 20 tons of concrete, leapt into the air, and rebounded to the side of the road. We didn't know what we'd find when we reached the wreckage.
Now, let me be clear. This would be a bad accident. The passengers are going to be injured. But I want you to notice some interesting stuff they've done here.
Steel cage has certainly done its job really well. You can still see the original shape, just that one nasty kink there. Don't forget, this is a car without a roof. The plastic was just shattered. So without even the strength of the roof, there hasn't been that much fit. You can in fact open the door.
That right there is impressive. Would firefighters need the jaws of life to cut you out to get paramedics? No. The paramedics could access you directly. Right there, you've saved a lot of time in first intervention right away. So, okay. What did I say the crumple zone was? Watch.
Bits fly out. And so anyway, when you come around the front, you do see that.
There's the crumple zone. Okay? That's what lengthened the time of collision, at least by a little bit. Again, in the smart cars, you're stuck. There's not much room to work with, but they figured out something.
Massive impact. On the other side, though, it still looks remarkably like a smart car. You can still full shape of the door. Indeed, the door not only opens normally.
So there again, the passenger, the firefighters or the paramedics can get instant access to the passenger, probably get the passenger out. That's some pretty good engineering. I'm not saying that if you crash a smart car at 70 miles per hour, you're going to be walking out of there happy and, no problem. I am saying they worked with what they could. They worked with what they had. Okay. Toilet paper physics. What? Yeah, there's physics everywhere. If you've ever been using a public restroom, you might have seen the massive toilet paper rolls, the really, really big ones. Okay? You might have noticed, especially when the rolls are near full, if you pull really slowly, the paper doesn't rip. But if you yank on it, the paper rips. Pardon me? Especially at an angle. Why? They're fairly frictionless. Like those axles are okay. There's some that are damaged. You know, you see, it depends on which bathroom you're in, but generally they turn okay. It's a good thought. It's actually something more basic than that. It's inertia. It's really, really similar. Who did I do the jug of water with? Okay, it's really similar to why Ashton stayed dry when I did my version of the magician yanking out the tablecloth. If I yank really fast, the water has so much inertia that it hardly has a chance to move before the paper towel started to move. If you yank on the toilet paper roll really fast, the toilet paper roll has so much inertia, the paper will break before the toilet paper starts to spin. If I had pulled on that paper towel very slowly, you're getting wet. You're getting soaked. If you pull on the toilet paper very slowly, you can usually overcome the inertia and get it to move. In fact, there's a really, really neat demonstration you can do here. This is from MIT. What we're going to have is we have a wooden block suspended between two strings. One string is on the bottom, one string is on the top. And depending on how we pull, we can decide which string, which thread we want to break. If we yank really, really quickly, which thread do you think will break? Now, it's tough to see, Hannah and Evelyn, you're in the back row. There is a very, very thin thread holding it right there and another thin thread dangling there. This is just a safety cord so that it doesn't come smashing down, but it's not part of the question. If I want to break this thread right here, the top one, pull very, 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 very slowly and gradually increase the force, or yank really quick. If I want to break the bottom one, pull very, 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 very slowly, or yank really quick. Toilet paper physics. Let's find out. So we have a wooden block hanging from a very thin black thread and a safety line. Identical thread down there. So we got one thread. We're going to give it a quick yank. Because that block had so much inertia, it really didn't have a chance to even start to accelerate before the thread broke. The same way when you yank on the toilet paper really quickly, the toilet paper will rip before the roll starts to roll. Pull slowly, the top one's going to break. Go. Pull slowly, the toilet roll will start to unroll. Is that all right? I could have stuck that in the forces unit. I stuck that in here because you may have noticed impulse force times. We're still talking a lot about forces as well. Is that okay, Jordan? Okay. Here are two fancy physics words that you need to know. I won't ask you to define them, but I will use them in questions and you'll need to know what they mean. There are two main types of collisions. There are collisions where the objects bounce off each other after the collision. This is what you were asking about the other day, Davin. A good example, curling rocks, they don't stick together. Billiard balls when you're playing pool, they don't stick together. Baseball and a bat, the baseball doesn't stick to the bat. Some car crashes, not all. There's a fancy physics word when they bounce off of each other. First of all, do me a favor, if you don't mind, underline the word bounce off, or the phrase bounce off. When they bounce off, we call them elastic collisions. If I'm giving you, Lean, a physics word problem and I say two cars collide elastically, what I've just told you is they did not stick together. The opposite is inelastic. When the objects stick together after the collision, if a football player tackles and wraps up and holds on to the person they're tackling, a dart hitting a dartboard is a great example, assuming the dart doesn't drop out, but a dart sticking into the dartboard or arrow sticking into the target. Some car crashes, because sometimes the wreckage does stick together. A bullet entering and sticking inside a target, we call these inelastic. What words did you underline, Hannah, who's not typing like mad on your phone? What words did I underline? What two words did I underline in point number one? Elastic, bounce off, rubber band bounces, elastic. That's how everybody has been remembering it for years and years. An elastic collision, I always think elastic bands, rubber bounces, they bounce apart. Inelastic is the opposite of elastic. There's a bit of a problem here, though. If I talk fast, sometimes I really talk fast, sometimes I really talk fast, sometimes I really talk really fast. It's hard to tell the difference between elastic and inelastic. It's hard to tell the difference between the word elastic, especially if I say there was an elastic collision and there was an inelastic collision. So I'll emphasize it. You're going to notice it's going to sound weird, but I'll say there was an elastic collision. I'll put a big pause in there, or there was an inelastic collision. I'll just try and make it clear. But if you're not sure, ask if you didn't hear me. Usually in the word problem it'll say. So if it says inelastic, you can assume they stuck together after the collision. If it says elastic collision, you can assume after the collision they bounced apart. Put your pencils down, look up. I have some video examples for you. I'm just going to freeze the screen for a second. Of several collisions. These are lab cart collisions, and your job is going to be to try and figure out. Oh, this is going to be irritating, Mr. Dueck. Let me pause the video for just a second. Collisions. First of all, you need to decide, are they elastic, Maya set up, or inelastic? And I'm going to tell you, they're going to be little lab carts that look identical. Sometimes both will have the same mass. Sometimes one will be heavier than the other. Your job is to see if you can use what you've learned about conservation of momentum to figure out which one is which. Let me show you what I mean. Boy, I'm so worried this is not going to work. No, I want to do this. Good. Thank you for letting me change. Good. Here we go. Here's an explosion. There's the first explosion. I'm going to do it again because Lean wasn't paying attention. Look up. Here's the first explosion. Okay. And here's the second explosion. In one of those, both masses were the same. In one of those, one was a heavy mass, one was a light mass. Let's watch them again and see if you can figure out which one is which. So here's the first one. Here's the first one. Do it again because all of you got distracted. Here's the first one. Identical masses or not? What's your hint? If the masses were identical, what else would be identical? I got to be fussy, not the acceleration. Velocity, because momentum is mass times velocity. That's what we're looking at. Yeah. Okay. Which one's heavier, the one on the left or the one on the right? Which one's heavier, the one on the left or the one on the right? The one on the left, less velocity, more mass, same momentum. How do I know? Because what's the momentum of everything right now? Be obvious. What's the momentum after the explosion? Still zero. That's momentum has to be conserved. So if the heavier mass goes this way, it's got to go slower. The lighter mass has to go faster because lighter mass times bigger velocity, smaller mass times bigger velocity equals bigger mass times smaller velocity. Okay. Number 3. Was that collision elastic or inelastic? Okay, you're going to see 3 elastic collisions. One's going to be same hitting same, one's going to be small hitting big, one's going to be big hitting small. I've randomized the order. Your job is to see if you can figure out which one is which. So now that you know what you're looking for, here's the first one. Here's the second one. Here's the third one. Which one of those looked fairly different from the other two? Was there one that stood out? The middle one. Let's look at the middle one. That was this one here. Why did this one stand out so much to you? What do you think that one is? You think they're both the same? If they were both the same and this was perfect, what should actually happen? The first mass should what? Come to a dead stop, and the second mass should absorb all the momentum, and since it has the same mass, should take off at exactly the same speed. I don't think that's happening here. Yeah, I think this is light hitting heavy. Okay? Heavy enough that it almost bounces backwards off. It does a little bit. So now let's look at the first one. Is that heavy hitting light, or is that same hitting same? Yeah, I think the second one took off faster than the first one came in. You got to watch close, but I think so. Yeah. And so the third one should be same hitting same. Ideally, we should see it come to a perfect stop and the other one take off at exactly the same speed. Pretty close. Pretty close. Of course, you're not on your phone right now. That would be extraordinarily foolish. Face down. What kind of collision were those where they came apart? I bet you the next few are going to be inelastic. They're going to stick together. It's going to be the same question. It's either going to be same hitting same stuck together, light hitting heavy stuck together, or heavy hitting light stuck together. Again, I've randomized it, Cody. Your job is to figure out which one is which. Hmm. Not much there for me to work with. I need a comparison. Let's see all three data points so we have a reference. Was there any of them that stood out more than the others, Maya? The most recent one? You think this one is heavy hitting light? What would heavy hitting light behave like? Think about, let's suppose if you were to tackle a toddler at full speed, okay? What would happen to your speed as you hit the toddler? Would you slow down dramatically or would you barely slow down? So I think heavy hitting light, I'm looking for one that barely slows down. That's the second one. First one, let's see. If this is heavy hitting light, it should barely slow down. I think that's heavy hitting light. It slowed down a little, but not by much. Yeah, I think this is a toddler trying to tackle an adult. Okay? Barely any moment. Well, all the momentum was conserved, but the mass got so big, the velocity had to get small. Maya, I think the third one now, I think it's equal hitting equal. Let's see. What that should mean, by the way, is it should move off at half the speed of the incoming because the mass technically doubled, and so your speed gets cut in half. Let's look at it again. You agree? I think that's same hitting same. Okay, so we can start to recognize this in collisions, in crashes. We can start to apply this. Let me hit pause on the video for a second. We're going to pause here. Tomorrow, we'll pick up with this lesson. These are the questions you'll see on your test for momentum for collisions. Word problems. I'm not going to give you the pictures like yesterday's lesson. Those are a pain to do. I'm going to give you word problems, and we'll look at 1, 2, 3, Only 3, and give you lots of practice as well. Friday, we're going to be pressing pause. Friday is going to be getting everything done so you have no homework for the weekend. Let me hit stop.